Is it okay, sir?
Okay,
Okay.
sir. Okay.
Okay. So yeah. So I will start with my company introduction, and I think the introduction regarding myself is given by the sir. So I will just introduce my company, and we'll go into the topic. Okay. So yeah. So Insta 3D Technologies is a 3D printing firm which operates on under five verticals. It is located at Coimbatore, Kerala, and we work for the passionate professionals who are who are experts in some diverse fields of engineering as well as in prototyping. So we provide the services to medical, automotive, industrial, architectural, engineering, and educational institution and organizations. And we are specialized in 3D printing. Considering my experience, I'm almost having 6 years of experience in 3D printing, and he's having an experience about almost about 5 years. So we started the firm in the year 2016, and it was we initiated with 3D printing services, and currently we are one of the major manufacturer of 3D printers in South India. We manufacture machines in FDM and SLA technologies, and we have 3D printer sales as well as training programs conducted to professionals in industries as well as institutions. So coming to the topic like introduction to 3D printing and its design, I will start the session with mechanical engineers. So you should know what is manufacturing process. We all know what is I look for an interactive session. So if possible you can interact with me, because it will be more convenient for me also, because one way talking and having interaction, this will be having a good conversation or a presentation. Okay. So like a manufacturing process is a process in which we make an object, we process an object with the help of technology. So you can directly classify a manufacturing, and the second one, additive manufacturing. As you all know, subtractive manufacturing technique is a traditional one, and we all have seen this technology at your colleges, many industries, and even you have experience directly through your laboratories or some experiences. So subtractive manufacturing is a process by which 3D objects are constructed by successive cutting of material, or it can be a removal of material. For example, turning operation, drilling are called subtractive manufacturing, because here we are making an object by removal or cutting of material. So this subtractive manufacturing is a vast area, and even in the mechanical engineering course itself, you have a manufacturing technology course. In the mechanical engineering discipline, you are studying MFT. So in that MFT, you are studying mainly studying 80% of the content is about subtractive manufacturing. So this subtractive manufacturing can be done by manual cutting, or you can do it by automated methods. It is called a CNC, computer. It is linked to a computer, and the CAD design converted into G codes and M code, and this G code and M code is processed by CNCs in order to get a 3D object. It is completely a programmed one. In similar manner, you can see additive manufacturing is an emerging segment in the manufacturing, and it is also called a rapid prototyping. And as its definition, it is a process Additive manufacturing uses data computer aided design or data which are processed in a software, and it is transferred to laying layers over the layers. It makes or it process an object, 3D object. So here you can see in the animation, like in the left hand side, it is a material removal process and it is called a subtractive manufacturing. In the right hand side, you can see a 3D printer which makes an object by laying layer by layer. So in the mid is a subtractive manufacturing process in which an object is created by removal of material, and considering this process, the wastage of material is more compared to additive manufacturing. It is called a scrap. Most of the processes in subtractive manufacture, the scraps are recycled. For example, in foundries, in aluminum fabrications, cutting process, turning process, drilling process, all the waste materials are recycled again. But considering additive manufacturing, that is B, the raw material, additive manufacturing process, we get an object and the wastage is very minimal. Even that wastage can be recycled. So, like, I will just brief the history of a 3D printer. So, the 3D printing was the technology. 3D printing was invented, like discovered on 1981, 18th century, and it was invented by Hideo Kodama, and he published a paper in regards of rapid prototyping and its process, that is called polymerization. In 1984, Mr. Charles Huck, he invented the stereolithography that changed the face of 3D printing technology. So it was the first machine. It starts 3D printing, like converting a digital model into a physical object. Then in 1992, Bill Clinton created the world first stereolithographic apparatus, and DTM invented SLS technology. SLS means selective laser sintering. It is a powder technology, and SLA is a liquid technology. And in the year of 2010, like, humankind started making organs and organ parts with a 3D printer by compatible materials on everything. And currently, I am doing research in that segment, bioprinting. It is called bioprinting. And in 2011 and 20, like, the 3D printing technology is coming as a future technology, manufacturing process, and especially in customization and personalization. It is implementing it in everywhere, in biomedical application, automotive industries, educational institutes, then research institutes, everywhere it is implemented. Like, it is in a growing stage. So what is the power of a digital manufacturing? Actually, additive manufacturing, 3D printing technology comes under a digital manufacturing process. So if you consider the overall population who are dealing with the manufacturing, 1 in 3 believe 3D printing will become more important than a traditional manufacturing, because 3D printing is having more advantages considering traditional manufacturing. 11% of population believe that 3D printing is ready to produce end use part, because the object which you are making used as a functional product, or can be used in a functional prototype or even real systems. Okay, the 76% of population in manufacturing agrees that 3D printing represent a more sustainable manufacturing method. sustainable in the sense its material, processing, and also its usability. So these three are the major benefits, and we have some more advantages for 3D printing technology. Degree of freedom, customization and personalization potential, faster into market, product faster into market. So 3D printing provides you a freedom of designing. You can design anything. You can design any complex shapes or any on any materials and you manufacturing. If you are going for designing and manufacturing of propeller blades or something like that, it is very difficult in making in traditional manner, but it is very easy to make in a 3D printing technology. And customization, personalization potential. So in 3D printing, every object you are making is a customized one. You can have changes in every product what you are making in a 3D printer. Sorry. But in a traditional manufacturing, even if you go for injection molding or some die casting or something like that, all the object you are getting is same. It is a copy of every product you can customize. And the best benefit of a 3D printing, it is faster to market, making the product faster. To reach the product, technology is called a rapid prototyping. So now we'll have a briefing in 3D printing technology. What is 3D printing technology? So as I mentioned, 3D printing is also called additive manufacturing, and it is a process of making 3D or three-dimensional solid object from a digital file. That means digital file in the sense you can use CAD or even you can use a scanned data. The creation of 3D printed object is achieved by additive manufacturing process in which each layers are laid on through a nozzle, and by successive addition of each layers will lead to creation of the object. So here you can see in the system left hand side the system slice. It is called a slicing processes, that is a CAD design or a scanned design, and it slices transfer the data to a 3D printer, and the 3D printer make the object by laying one over the other. So the basic anatomy of a 3D printer, like the main part of a 3D printer is an extruder, and there will be a bed. This extruder moves, and the extruder, or it is called a head, and the head moves along the path where we have generated the G code and M code and generates a 3D object. I will just show you how it works. 1 second.
Hello, sir. Video not visible, sir.
1 second, sir.
Check it, sir.
Okay, 1 second, sir.
Okay.
I will play it.
Okay, sir.
Is it visible, sir? Is it visible?
Visible, sir.
Is it visible,
Visi-
sir?
Visible, sir.
Hello?
Yes, sir, visible.
Okay, okay.
Visible, sir. Visible.
So this is the nozzle or extruder. It is an extruder,
Sir,
and the
PPT
blue
not clear,
color
sir.
is the material which we are using. It is called a raw material, or the video is visible. So this is the second layer. So this extruder will have a nozzle at the end tip, and which controls the thickness or thickness of the layer. So this is how the 3D object is created. So that is the process like behind a 3D printing technology. The material, raw material can be a metal or a plastic material or a polymer material, anything it can be. And that process is called FDM, fused deposition modeling method. So I will come into the process. Is it audible, everyone? Like is it audible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Okay. Yeah, okay. And the presentation is also visible now, sir. Presentation is visible now, sir.
Yes, sir.
Yes, sir.
Okay, sir.
Hello. Yeah, okay.
Okay.
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay. So this
Yes, yes,
the
visible.
now I come to the 3D printing process flow. 3D printing process flow. So in the first, making ideation means making an idea or a thought. So there are even that ideation concept is also a big vast area, and it is called a design thinking process. Like you have, I think you have heard about this design thinking, and and it have many methodologies. It have many iteration stages in ideation. So ideation means, I will just explain what is ideation. Ideation means figuring out what kind of object or what kind of output you require. So that is called ideation. So from that idea, we'll have brainstorming. Brainstorming means we'll go or iterate many things and regarding our requirement, like specific required specifications, and we'll come up with a model. Maybe it may be a sketching, or it may be hand drawn, or some concepts, and we have to convert that concepts into a 3D model. And this 3D model can be a CAD design, or it can be a scanned model. We can use scanners. We can take the data through scanning process as well as by computer aided design process. CAD means you can use there are many designing softwares available right now. So you can design in any of the softwares, and you can convert that design into a 3D printable file. And that process is called slicing. Using a slicing software, you can generate G code and M code, which is a language for a 3D printer. Okay. So this slicing process, after slicing, that designed model is sliced into thin layers. That means we are just slicing, what we are doing in like slicing of fruits or vegetables. Similar manner, the software slices our model with a set of parameters. In the upcoming slides, I will brief you regarding the parameters and its design factors. Okay, so in this, after slicing, that sliced object is called, it will be in a STL format, stereolithography or standard tessellation language. And this is uploaded to 3D printer through many modes. Like you can directly connect a 3D printer with your system through Wi-Fi mode, or you can transfer the file through Ethernet, or you can transfer through memory cards or USB or anything. After transferring, we have to select or choose the material what we are going to print. If you are choosing an FDM technology, all the raw materials which you chose is in filament form. That means a solid raw material in a wire form. If you are choosing SLA, stereolithography apparatus, SLA or DLP printers, the raw material which we are using is a liquid kind of thing. If you are going for SLS technology, SLS laser sintering technology, the raw material for SLS is powder kind. If DLMS, in DLMS method, we uses metal as raw material. So here, after uploading, we will choose, and the machines also varies according to the material what we are processing. So here I chose a filament. The filament is a raw material for FDM technology, and this filament is loaded to, at the color or the material. In even in FDM, there are many combinations, and this is fed to a 3D printer. And after 3D print, feeding that 3D printer, this 3D printer operates on the G code and M code from the STL file, what we processed in a slicer, and it starts printing. There are many printing concepts also. In the upcoming slides, I will explain in that also. After printing, we get the output. We remove the object from a 3D object, or the required model, the part from the 3D printer, and we take it for post processing. There are also many processing technique based on its materials. Okay. So now come into design guidelines for a 3D printing. So it is very important, and this is a guideline made by 3D Hubs. 3D Hubs is a international website which is handling most of the advanced technologies, not only 3D printing, but also many other processes also, powder technology, CNC, and many 5-axis, 6-axis, 3NCs, and everything. And they serve all over the world. Like, they are providing service all over the world. Even we can have orders or service orders from here to their website, and they will make the object, and they will ship to us. So based on them, I formulated the design rules for the 3D printing. And the first one is the supported wall. And the supported wall condition is like, for FDM, the wall should be of minimum 0.8 mm thickness. And for stereolithography, SLA or DLP, the wall thickness should be a minimum of 0.5 mm. And there is one more constraint, and the supported, why it is called a supported wall? Because the wall should be held by any two other walls. It should be a supported. Unsupported wall means it is a stand-alone wall, and based on FDM technology, if we are going for a design, we should maintain a 0.8 mm of minimum wall thickness in order to get a good surface finish in an FDM technology. And considering SLA technology, it should be 1 mm. Then another segment, a parameter, is support and overhanging. It is very important part in a 3D printing slicing technique, because supports, like, even if you consider a house construction, if you want to concrete or make a slab or some roof, we need to create supports. If there is no support, it will fall down. Similar manner, in 3D printing technology also, there will be some overhangings, and these overhangings requires a support, but on some constraint. If the overhanging is less than 45 degree, it requires supports. But if it is equal or less than, like in 45 degree, it does not require a support. Okay. Then emboss and engraved. Embossed means like projecting some parts above from like a plane. That is called embossing. And engraving means a depression. So there is like a constraint for FDM, that means 0.6 mm wide should be there and 2 mm height should be there. It should be maintained strongly in FDM technology, and in stereolithography it should be 0.4 mm and 0.4 mm wide and height. Okay, both. Then there is another parameter called horizontal bridging, and horizontal bridging means without support it should have a bridging effect. So in FDM 10 mm is the constraint, and holes, maintaining holes tolerance, it is about 2 mm, and connecting or assembly, the tolerance is about 0.5 mm, and it should be maintained in assembly of system. Like if you have an assembly design and if you are going for FDM technology, you should at least maintain 0.5 mm tolerance in the mating parts. Then all others are not that much important because I have already covered in the first 6 or 5 parameters. And the left bottom, you can see a 3D, that means the dark color, black color is a 3D model design, which is having a curvature, and the output 3D print, that blue color is an output of a 3D print, and you can see a like zigzag structure or a step structures, and which is obtained due to laying layers by layer, because if this can be controlled by maintaining the layer height. Okay, so if we are keeping in this orientation, that first orientation, it will form z-axis layer steps, but if we are making it vertical, the steps are reduced, but it will compromise, sometimes compromise its strength, sometimes compromise its profile, everything. So there is some parameters or constraints for controlling that also. So like, and also while you are going for a design, in the right end you can see a square boxes, and in that square boxes the box should be a solid surface, so solid part, and it should not be a surface means only a thin faces will be there. It should not be a hollow one. A hollow one should be completely packed with the material while you are designing, and if there is any surfaces, it won't print or it won't be considered in a slicing software. And the minimum wall thickness we should maintain for a good print is, wall thickness is 1 mm. Okay, so the 6 major design rules to remember while printing are: first one is no supports needed, because when we are going to design an object, or when we are converting an idea into a 3D model, we should consider that I should design, or you should design the product with a minimal support. It is said because if we have a more supports, the finish of the end product will be compromised, or we will be having some tolerance or some precision effects on that. So the second one is the minimal feature size. That means even the very smallest feature what you are having in the design, it should be it should be more than 0.8 mm. At least we should maintain 1 mm, because below that the slicing software will not consider it. And also there are some machines, 3D printers, which is printing in high precision and which are costlier. Here these design rules are formulated based on a commercial printer, but there are many research printers which can even perform below 0.5 mm. Okay, so the minimum detail size is like 0.25 to 0.6 mm. It is recommended because in XY axis. And the fourth one is like moving part, or that assembly components. Moving part means assembly or some fit components. It should maintain a 0.5 mm tolerance. Okay, then wall thickness minimum of 1 mm, like 0.8 mm to 1 mm. Then escape hole is there. It is considered like if we have some closed solid part, we should create some escape holes to remove the support material, or stuck material or something like that. Okay, so this is the six. These are the six main design parameters we should consider during while we design for a 3D printing. Okay, it is compulsorily maintained while we check for a 3D printing services or 3D printing. I think the video is not. So just see this how we convert an idea into a 3D model and then making a 3D object through a 3D printing considering this design. So this man is designing a model, a toy or something like that, a rocket model. He's designing it in software CAD design, and he bring into a slicing software. This slicing software is called Cura, and this machine is Altimaker, an FDM 3D printing machine, transferring the data to SD card. This is the filament. This is the raw material, and it starts printing. And now the video is in time lapse, so don't think that it will complete in minutes. Sometimes it may take in hours. It's shown that yeah. Now it starts. So this is how an object is created by using a 3D printer. Okay. Now there are many technologies in a 3D printing additive manufacturing process, and I showed up an example in FDM technology, and I will just brief. I'll give a brief regarding this technology, basic types of 3D printing. The first one is an SLA 3D printer, and this SLA 3D printer operates with a liquid resin as a raw material, and a laser will pass over the liquid resin, and where the laser are in contact with the resin, it solidifies, and the resins are called photoresins. And coming into FDM technology, fuse deposition modeling method, and as I have showed you, we uses a solid filament form of raw material, and these filaments are completely a thermoplastic material, and there will be a bed, and it starts printing through an extrusion nozzle and extrude, and it is called extrusion head. And even you are having some machines with multiple heads, and which where you can process multiple materials simultaneously. And the third one is DLMS, and where a powder material, metal powder materials are used as a raw material, and high-end lasers you are used to melt and making it solidify, and where the laser are in contact with the powder, it solidifies. And SLS is a selective laser sintering technique. And here it is also powder materials are used, and most of the raw material are polymer material. And similar manner, a high-end laser is used to cure the powder raw material, and where the laser come in contact with the powder, it solidifies, and you can get the object, 3D object. And other than that, these all are basic types of 3D printers what are commercially available. And now the researchers are going in researchers, as well as there are products in advanced 3D printing technology. And the first one is the bioprinting. And here we uses bio inks as a raw material. And in bioinks, there may be like tissues and cell generation components. And we use currently it is in test. And we are developing some biomaterials as well as bio ink for directly having test in human. Okay. So there are two kind of bioprinting, using biomaterials, like in vitro and intro concepts. And these are in research right now. Even some in US they have developed cornea eye lenses by the method of 3D printing, bioprinting. And the second one is 3D printing in field of construction, and it is already implemented. And in China, they have made houses and hospitals, houses they are making within a day of time. Within a day of time, they are making a house with use of a 3D printer. And during the COVID situation, Corona situation in China, they have built a hospital within 14 days. Okay. Then the third one is a PCB 3D printing, where we can print a PCB circuit, like a circuit. We can make a circuit board, and which can be used for electrical purposes. So it is now in a developing stage. Then food printing, and it is right now in a commercial stage. The printers are commercially available right now. You can use any products, any food product, and you can make any design, and you can print it. You can have the printed part. That is the concept of food printing. Now coming into slicing. So as I mentioned, there is an intermediate between a CAD design and a 3D printer. Slicing or slicing software is is an intermediate to convert the CAD design into a machine language. That means the slicer convert a 3D model into an STL, standard translation language. That means G code or M code, and is provided to a 3D printer. So when you are considering a 3D printing, there is a basics for that. That means like we should have, as I mentioned, we should have a blueprint. Blueprint means a CAD design, a CAD model. It can be from CAD design, or like a 3D model. It can be from a CAD design, or it can be from scanned data. And by using a slicer, this model is sliced into thousands of horizontal layers, and this slicing layer is transferred to a 3D printer, and the 3D printer operates on that. How it is doing, like each sliced layer, like if you number 1 2 3 4 5 6 in the sliced as like sliced layers, and that each number will be processed like in that same order, 1 2 3 4. And this first slice of layer will be having its own G code and M code. And after completing that G code and M code, it will the head will raise, and it start printing the next layer over the bottom layer. So this is the basic process. So as I mentioned, like there will be a slices, there will be a model. We will slice into thousands of layer. It start printing through a nozzle, layer depositing over another, and it forms a 3D object. So the basic 3D printing parameters. Okay. Everyone is audible now?
Audible, sir.
Yeah, okay, okay.
Sir, it's audible, sir.
Okay, okay. So now I come into 3D printing parameters. So we should maintain some parameters. It is compulsory to mandatory to maintain parameters while we are slicing an object in for a 3D printing technology. So the first one is the build size. So the machine settings or build size. If we consider a slicing software, the initial after the initial installation of the software of firmware, it will request for the print settings, machine settings. That means machine settings in the sense, what is the build area? What are the build volume it can print? What machine we are using? We are going to interface with the software. So these most of the slicing softwares are open source. Open source in the sense like you can use this software for most of the 3D printers. What are available in the market. Okay, so for example, Cura, Idea Maker, Astrobot, then Repeater Host, all these softwares are open source. It is called open source softwares, and you can interface this software into any of the machines 3D printers available in the market. Okay, so while you're installing or after your initial installation, it will request for the machine settings, and especially machine settings in the sense of nozzle size, the print area, that means build area, that is length, width, and height, and the type of printer. I'll just explain. There are four types of printers actually: Cartesian, Polar, and Delta, and one more is there, Scalar type, but it is considered under Polar right now. So type of printer, then that nozzle tip, what of nozzle extrusion tip we are using, and whether we are having heated bed or not. Heated bed means where we are printing the object. Sometimes we will use a heated bed because some material, engineered material, it requires heated platform for holding the material, and not having the wrappage. Okay, so I will mention everything in the upcoming slides. Okay, so these are the first initial sorry, machine settings what the slicing software requests initially. So if you consider the build size, there are many build size available in a 3D printer. If you consider an FDM printer, even we are manufacturing printer from a build size of 180 mm. 180 means 18 centimeter till 1 meter. That means 18 centimeter build volume. That means 18 by 18 by 18 till 1 meter by 1 meter by 1 meter. This is in FDM technology, I'm telling. In SLA and SLA technology, it starts from 100 to 300 mm. 100 by 100 by 100 till 300 by 300 by 300. So these two machines we are manufacturing, and in SLS and DLMS, the build area, build sizes, it varies according to the machines or according to the brand we are using. Okay, so the first one is the Cartesian type, and normally we call the Cartesian type as a 2D print, like a 2.5D printer, because it is not completely a 3D printer, but it is not a 2D printer also. So we call it as a 2.5D because, like, if you consider the printing, initially the head will be fixed to a two vertical poles, and this head, the movement of the head, that z-axis movement is controlled by the end rods, that two end rods, and initially it will print the base layer. After printing, it will like XY direction. The first print will be in XY direction. For example, as you saw in the video, the first video, the first layer blue color print will be in XY direction. That means a round surface is printed in XY. Then it will rise to a particular position. Again, it print in XY. Then raise in some amount. Then again it prints. So that is called a Cartesian type, like stacking over, like a notebook. You know how a notebook is. Like you can draw or you can slice pages of notebook one by one, and you are stacking. Same concept Cartesian printers work. The another one is Polar, or it is called a scalar printer, where the bed is also having a direction of movement. Here, the bed will be having, in polar kind, it will be having a rotational movement. In scalar type, it will be having XY movement. So that is why, since it is having a polar direction movement of the bed, it is called polar type. When it is having XY direction movement, it is called scalar type. Okay. Then the new and updated design of a 3D printer is called a delta type, and in delta type, simultaneously. Simultaneous motion will be there. So the pillars are assigned for the motion of the xn, and there will be arms which connects the extruder, that means the head, and the motion of the vertical pulleys on the vertical arms, three arms, controls the motion of the head, and it controls the print. The another print parameter is the build orientation, and this is also one of the important parameter. In this parameter, uh, in this parameter, hello, is it audible? Hello.
Yes, sir. Yes, sir.
Okay. One second. Just I will plug my system to power. 1 second. Hello. Yeah. So here the build orientation, like it can be determined by the position of the object. So we should choose which orientation is the best for the printing, which orientation is best, which will provide the best outcome. So if you consider this as ASTM standard dog bone shape specimen, the first one is kept in X direction, second one Y direction, and third one is Z direction. Here, if we consider the first one, X direction, the surface area with the build plate is very minimal. So there is a chance of toppling. That means it will be shifted. That there is a chance that the head itself hits the object and it get damaged. The print will damage. And the second one, Y direction, and where the surface area contact with the build plate is larger. And the third one, Z direction. In Z direction, the surface area is minimal and the height is much higher. So considering these three build orientation, which one is the best one? The best one is the second one, Y direction, because during 3D printing process, considering the build orientation, the conditions are we should have a larger surface area with the build plate, minimal support, and less Z effect. If you consider the first one, X direction, the surface area is less, so it is not recommended. Minimal support, it will be having support in the lower areas, and less Z effect. Z effect may be less compared to the third one, but even it is not recommended. The third one, you are having Lower surface area, not recommended. Support, the lower parts, it always has a support, so not recommended. And Z, not recommended. So the third condition is least recommended. The second one is the best recommended orientation. So now we will consider the build settings. The build setting in the sense, while we print, the user or the end user of the product can determine or can decide what all parameters I should have, what all build setting I should have in a 3D printer. So if you consider an object, let us consider this a rectangle object. And if you see the image, you will have a top layer, infill, outer shell, and bottom layer. So 3D printing technology is the only process in which you can control the aesthetics or and as well as the infill of the product. No other traditional manufacturing process can control these parameters, this much parameters. Okay. So the 3D printing is the only technology, manufacturing technology can control more parameters during a manufacturing process. Okay. So the first one, the top layer, even the top layer you can control whether it can be 3 layer, 4 layer, 5 layer, you can control in a 3D printing. You can control the infill parameters. Infill means like whether you need the object as a hollow or you need some material inside that to have some strength. If you need completely, and if you are going to use the product completely as a functional part, you can use it with 100% infill or 90% infill. Then outer shell, even compromising the infill, you can improve the strength of the object by increasing the shell. It is similar to a wall of a house. If you consider a room, you will have walls in 4 sides. If you want to increase the strength, you can increase the thickness of the wall. It is not compulsory that you should create some support or beams or columns for a room to improve the strength. You can also increase the outer shell thickness so that it can have better strength. Then similar to top layer, you can also control the bottom layer also in a 3D printing technology. So in the right hand side, you can see infill and the shell. And infill, you can control from 0 to 100. Any infill, even you can control the infill structures. And the upcoming slide, I will just mention you what are the infill parameters you can set, what all the infill density you can set, what all the structures, infill structures you can have in a 3D printing. Okay. And number of shells, if you consider shell, 1 shell, 2 shell, 3 shell, 4 shell. It depends on the requirement. 30, 25 shell, 30 shell. So if we give 100% infill, it is not required. It is not mandatory that we should give more shells because 100% means 100% material inside that. So there is no possibility of giving shells again and again. So it will not affect the strength of the material. So infill of the parameters. So if considering infill of the parameters 0 to 25, I just shown some specimen which is having infill of the parameters 0 to 25 percentage. So this is also called infill density. So if you are going for a prototype or something like that, for a demonstration or some prototype or something like concept model or something, you can go with 0 or 5 or 10 percentage is recommended, because you don't, it may be an iteration, design iteration, or it may be a concept model. We don't know whether it is right or wrong. We are just printing it for an experience. In that cases, we have to reduce or we have to minimize the wastage of the material. So in that consideration, we can go with 0% infill, 5% infill, 10% infill. Okay, so we constrain the use of material to a minimal one. So it cannot be attained in any of other manufacturing technologies, traditional manufacturing process. But if you want to print an end use product or functional product, you can go with 100% or 90%, what you recommend for the product. Okay. And based on this infill percentage, the time of print also varies. This infill, so this is steady, like the green color denotes the best and the red color denotes the worst. So if you consider strength parameters, 0.1 mm thickness with 10% of infill is the worst, and 0.3 mm with 100% infill is the best. Considering infill, you can see that the graph goes along. So like quality wise, if you go like lower layer height, the quality of the print will be more. It can obtain a good curves, profiles, and also good strength. Then cost also vary with time. So like if we go with higher layer heights, it is like in regards of cost and time and size of layer height. I can just give you an example, like building a wall with a red brick, building a wall with hollow brick, bigger size. So if you are going with building a wall with a red brick, in order to compensate the size or compared to the size of a hollow brick, you may need 2 or 4 blocks to reach a one hollow brick. Okay, so in that method, laying down the hollow bricks construction will be faster compared to the red brick. So the time, the cost related to layer height can be related to this type of construction, this type of construction model. So this is a graph in which I just constrain the speed to 60 mm per second, layer height 0.2 mm, temperature 195, that is a PLA material, polylactic acid material I used in this iteration, infill parameter linear, then number of shell used to 2. So here if we consider the maximum stress compared to infill percentage, if you give 100, it will have more strength. If you give 10%, it is very minimal. The strength it can attain or bear the load is minimal. Print time and infill. As I mentioned, if it is 100% infill, it will take more material, more time, more cost. It is less infill, less time, less cost. Elongation of break is similar, like it will 100% will be having more elongation compared to the lower. So this is another in regards of its structure, linear, diagonal, hexagonal structures, means like this is the infill patterns. So here you can, in the left hand side, you can see Hilbert structure, Archi structure, octa structure, then honey structure, line structure, grid structure, rectilinear structure. All this structure determines its strength as well as load bearing capabilities. So comparing that structure, I have plotted a graph. In this, maximum stress can be withheld by linear and hexagonal patterns, and elongation break, it can be held by diagonal structure. That means diagonal means the line itself, it can be it is in rectilinear or line, it can be a diagonal one. So this is the infill pattern, and this infill pattern it mainly determines the strength without compromising its infill. So as I mentioned, the shells, the definition of the shell, like you can increase the strength of or improve the strength of the component by increasing the number of shells without compromising the infill density. So first one is the 2 shell, second one 5 shell, third one 10 shell, 15 shell. So this 15 shell or 10 shell will be having more strength, and here I have given only 5% of infill without compromising, without increasing the infill. If I increase infill, more material will be consumed, but without increasing the material, I have just increased the shell. So this method also you can lower the wastage of the material without compromising its strength. The third parameters, the third important parameter is the layer height. So layer height is the one of the major parameter we give in a slicing software, and this layer height determines the quality of the print also, the surface finish of the print. Okay, so the layer height determines the height of each layer. That means it can vary from 10 microns 50 microns. In FDM printer, most of the commercial machines start from 50 microns till 400 microns. If you go with the SLA or SLS printers, it starts from 30 microns, 20 to 30. Even 16 microns are available for high-end precise materials machines. 16 microns till 300 microns are available. So you can see the picture in that the layer height are always mentioned in z-axis because laying layer upon another. So that layer, individual layer, it is called layer height. So you can see like 30.30 mm is that it is called a 300 microns. So in that constraint, you can see comparing 0.1 mm. That means 10 microns. It may have 3 or 4 layers to attain 0.3 mm. So the printer head have to move 3 times to reach 0.3 mm specification. Okay, that layer height. So it takes more time, and material consumption is almost the same, but in also accurately comparing this to 0.1 and 0.3, there will be a slight difference, and that 0.1 will consume a bit more material than 0.3 because there will be some overlap or overlap of the layers on one another. So here laying one layer in 0.3 mm will be equal, it will not be equal to the material consumed laying 3 layers. So this is an example for that. So if you consider 0.3 mm, it takes only 8 minutes, but going on 0.2 mm layers, it takes 11 minutes. If we are going for 1 mm, it takes 23 minutes. That implies if we increase the layers, the time consumption will be low. If we reduces the layer height, the time consumption of the same object or product will be higher. If time is higher, the cost of the product is also considered higher. So similar manner, I have compared the layer height with the strength, time, and the consolidated report is the below one. Same parameters, like I have set 60 mm per second as speed, infill 80%, temperature 210 degrees Celsius, and the infill parameter, like infill pattern is linear, and number of shell is 2. So considering that, you can see that 0.3 mm, 0.25 mm is possessing higher strength compared to 0.3 and 0.1 mm. Because of this, normally in every commercial printer, we uses 0.25. That means 250 microns layer height. Normally, we also print the object in that parameter. Only when we require more high precise or high accurate dimensions, we go with 0.1 mm. Then print time also consider, like we have very least print time for higher layer height. and lower layer height, it take higher time. That means almost 68. Okay. So the next parameters is the print temperature. Print temperature varies based on its raw material we are using. So there are variety of raw material which can be used in an FDM printer, and all the raw material what we are using is a thermoplastic material. Thermoplastic means it can be reheated again and again, and while heating it deforms, while cooling it will transform to a solid. So here I consider, for the test, I consider wood-filled PLA where a wood particles are incorporated to a PLA material. PLA means material means polylactic acid. Polylactic acid. So like I have printed the wood-filled PLA with 250 degree, 230 degree, 200 degree, 190 degree, 180, 170, and 160 degree. And considering all the print, I came to a conclusion that 170 and 180 is the precise printing, because there are three concept of extrusion. First one is under extrusion, optimal extrusion, and third one is over extrusion. This under extrusion means because of lower temperature, it does not have proper extrusion. That means this also will lead to a clogging of material in the nozzle. Optimal extrusion means the required finish or quality of the product that is obtained at 180 and 170 degree. And in over extrusion, the material heats more than its required temperature, print temperature, and the material will flow like a fluid. So in that condition, it is called over extrusion, and it is attained at 250 and 230 degrees Celsius, and even 200 degrees Celsius. Some percentage of over extrusion can be seen. So as I told, like you can classify the FDM material into three stages and two categories. The first category, all these categories are included in thermoplastics only, and in thermoplastic itself, you can classify into two segments: amorphic and semi-crystalline thermoplastics. Amorphic thermoplastics are polymers having a random order molecular structure. That means it does not have a proper molecular structure. Because of that, it does not have a sharp melting point. This kind of material are called amorphic. And this amorphic material soften gradually as temperature increases. Like it will be having, it don't have a sharp critical melting point. So that for a period or range of temperature, it softens and hardens. But in semi-crystalline, it is having high order molecular structure, and because of that it possesses a sharp melting point. Because if, for example, 160 means beyond 160 it melts, lower than 160 it is in solid state. So under that, you can classify the plastic into standard, technical, and high temperature plastics based on its melting temperature. This PP and PE material are known as standard materials, which are used as a basic FDM materials. And in amorphic materials, it's PPE, ABS, PS materials are used. If you go into some functional product or something, we use technical plastics. In technical plastic, we can use PC in amorphic. Most of them polycarbonate. PC means polycarbonate, and it can be used for a functional part. Then this high temperature plastic are PEEK, PET, then alchem, all these materials which is having the melting temperature higher than 300 or equal to 300 or higher. And these are mainly called as engineered plastic, and some of the plastics. Hello. And some of the plastics are like, hello, can you hear me, sir? Hello.
Yes, yes.
Yes, okay. Some sound are
Yes,
there,
sir.
disturbances are there, like,
Yes, sir.
okay. So high temperature plastics are engineered plastics which are especially using some plastics of this kind are even equivalent to metals also. Like altum or peak are currently using for some biomedical applications, and which are using for some implants also, some kind of implants, and researchers are going on that. Then the next parameters is layer addition, and layer addition means the addition of layer between one another. So if you see in the right end corner, you can see an image schematic diagram of FDM layer construction, and every layer is having a radii and a notch, and this cannot be eradicated in an FDM printing because it is formed due to the nozzle deposition. So the bond strength between the different layer is always lower than the base strength of the material. And the higher temperature and the pressure remelts the surface of previous layer, enable the bonding of new layer over the other. So this layer strength only affects in Z axis and in Z orientation. So that only initially I mentioned that we should reduce the Z height for getting a strength, a stronger part during 3D printing. The next one is the support structure, and considering this, like already I mentioned, like above 45 degree, we does not require support. If the overhanging is above 45 or equal to 45, we does not require any support. If it is lesser than that, we require, or the hanging part is above 45 degree, we require a support function. Having in state, so on bridging, it will fall down due to its gravity. And it is recommended that the part is designed in such a way that we should minimize the support structures. Now I will just show you. There are actually one more thing. There are two kinds of support structure. You can use the same material as support. The same material what we are using for the base material can be used as structure, support material, or you can use a water soluble or a different material as a support structure. Okay, so if you see this image, like orange is the base, the tree structure. Sorry. The orange color is the base material and white is the support material. It can be the same material, the white can be same the orange material itself, or it can be a different material, or it can be a water soluble material. So I will just show you an example of a water soluble support material. So this is a dual head nozzle extrusion system, a 3D printer. Here one nozzle is having the base material, the another one is having the support material. You can see a gray color and a white color. So the white is a support and gray is the base material. It's a time lapse video. Now they are dipping it in a warm water, like lightly warm water. So now it dissolves. The support structures dissolves. So this water soluble material is called PVA material. Okay. Now, like we'll have a discussion about the slicing softwares. I told you that it is an intermediate between a CAD design and a 3D printer. I will just demonstrate, or I'll just show you what all slicers what we
Sir,
are
one
using
minute.
in 20. Yeah, yes,
Sir,
sir. Yes, sir.
sir, voice break ಆಗಿದೆ.
Is it audible, sir, right now? Hello, hello.
Sir, is audible, sir, and the PPT is not visible, sir.
Okay, sir, audible, sir. Okay.
PPT were not visible. 1 second, sir.
Sir, next session start 12 o'clock, sir.
Okay, sir. I'm just concluding, sir. It's just a
Okay,
concluding.
sir.
It's almost
Feedback and
finished.
everything.
Can you see the PPT, sir?
Okay, sir. Okay.
Yes, yes.
Okay. So, like, I'll just introduce what all 3D printing slicing softwares are currently available in the market. And just I will the slicer, like as I mentioned, it is just to generate G code, and it is a programming language understood by the 3D printer. So this is the first one, the first and best of the printer slicing software, Simplify 3D S3D, and it is available with a license pack, and it is a paid version. And there are many we can alter many parameters even while printing. Like in between infills also we can control through slice 3D, slice simplified 3D S3D. So it is not recommended for an beginner, but it can be it is recommended for an expert or a commercial purpose, because as it is expensive, it is not recommended for beginners because they can have trials with open source softwares. The second one is the Cura, and Cura is one of the best and more convenient software what we are using, and it is almost compatible with all the printers which are available in the market. Most of the printers which are available in the market, and is completely free and open source. And there is even there it is, since it is compatible with all and the estimation is not proper, it has some errors, like mostly in time, showing the time, that estimated time, and also in some cases it's material consumptions also. The other one is Idea Maker, and it is more user friendly, as well as its visibility is more in, like you can understand the parameters very easily, and it is more convenient by user to use the slicing software in by Idea Maker. And it is developed by Race 3D, and it is also an open source software, and it is compatible with most of the printers available, even the Delta printers, Cartesian, and also Polar. Then Slicer 3D, it is also an open source software, and it is not recommended for the beginners because it is little bit complicated. Only those who are having a good knowledge in the parameters and the setting of these parameters can operate in this slicing software. Then repeater slicer, it is also majorly used software, and it is a cloud based one, free of cost, like open source, and and developed by RepRap. Like you can use this softwares for kit versions or your self-developed. Tracer is like the print quality is not matchable to other softwares because there is some degraded quality of print while you are using this slicer. Then Octoprint is another one, cloud-based, and it only supports STL, but it can be operated by your mobile or tab, what we are using. It does not require any systems, or it is not mandatory that we should have a system. And this Octoprint is working on basis of Cura engine, like. Then this 3D printer OS is a cloud-based. It is also cloud-based, and it is designed especially for student version as like beginners, and it is very easy. And we cannot provide a much of parameters in this software slicing software. Astroprint is also like it is Astroprint has developed an extra upgrade which can be connected interfaced to a printer, and you can operate like without a system or without a operating system. Like it is a standalone slicing system, and which have the Cura like slicing software in it, and it has some limited features, and it is a paid one. So it is also not recommended for a beginners, but it can be used by professionals. So finally, I was having a video, but I think it's time to conclude. Sir, do I have time to play a video? Hello? Hello?
Sir. Sir, next
Hello?
session to start 12 o'clock, sir.
Sir, no problem, sir. Then I
Okay,
conclude, sir.
conclude to
I conclude
clarification
my
of doubt and
slide.
everything,
Okay.
sir.
I think I have took a lot of time. Like even due to connectivity issues, also I took more time resolving that.
Okay.
I apologize for that. And thank you, Mani sir, and thank you, KSR College Mechanical Department, for giving a great opportunity, like having a talk like this with this much of candidates. And I appreciate KSR like initiating this kind of programs. Thank you, sir.
Okay, sir. Sir, wait a minute. If you have any doubt to clarify, sir. For participant.
Yes, you can have clarifications.
Sir, I have one question.
Yes, sir.
What is the minimum thickness we can print from 3D printer,
What is the minimum thickness for?
we can print from 3D printer. Means what is the minimum?
Like minimum thickness, theoretically we mentioned 0.8 mm, but practically it is 1 mm.
Okay, sir.
Yeah.
Hello, sir. I have one question.
Yes.
Is there any density difference between the
Yes,
material of the base and the support?
of course, if you are using a different material as base material and support material, it has density difference.
No,
For
even
example, if you are using,
okay.
yeah.
Sir, suppose if we are using the same material, then
Even
the
that is having because the like density in the sense in infill density, I'm telling. The support, even we can control in some slicing software, we can control the infill of the support material as well as the infill of the base material. If, for example, if we are giving the infill of base material like the main object 20%, you can make the support density as 80% or something like that if we are having more overhangings. So we can vary that also. It is also controllable.
Hello, sir. This is Professor Rao.
Yes.
I have a
Sir.
question for you.
Yeah.
Can we use the composite wire filament in FDM machines with different support materials?
Yes, already there are some commercial composite material available in the market. For example, PLA carbon fiber material, PLA ABS, the ABS carbon fiber material, PLA carbon fiber material are available in market. It is a composite material. You can use if you are using dual nozzles. If you are having a dual nozzle or an accessory called a pallet, we are having an accessory called a pallet. You can where you can feed more than two or three material in one push, and you can print in three or four materials simultaneously at a time.
Okay, means we need to just use the polymer for the
Yes,
specific extrusion, right? We
yes,
cannot
yes. Two
use
heads.
the metal kind of elements within the
Yeah.
filament, right?
There are some researches going on for this metals polymer composition, like matrix as a composite as metal and matrix as a polymer material. But the issue is like we cannot go with lower nozzle sizes.
Okay,
It will
because
have clog issues. Due to
yes,
some clog
because
issues, they are going with the higher sizes.
okay, because
There
we
is
have
there,
tried
yeah,
we have tried to develop the filament
yeah,
with a help of extrusion machine,
yeah.
but it is not possible. So I thought if there is another method, so that's why I asked.
There are some developments going on, like filament extrusion, screw extrusion equipments, like like where you can blend materials and you can bring it as a wire form. In that wire form, the constraint, only the constraint is that you have to maintain the wire form as if we are going for FDM printers, 1.75 mm nozzle size also you can use, 3 mm 2.85 size also you can use that filaments. So the diameter of filament should be maintained in a constrained manner. So in that cases, the clog issues can be controlled for an almost for a certain
Yes,
uh,
right,
yeah,
right.
yes,
Thank you, thank you, sir. Thank
Hello.
you very much.
yeah.
It is possible to convert single extruder to double extruder?
Yes, yes, you can do it with an accessory. There is an accessory called a pallet plus, and
Okay.
where that accessory itself act as a separate system, and in that accessory you can put four different material or four different color feed filament, and it can make it into one filament. That means it will patch the filament, join the filament, and feed that single strain to the single nozzle machines. It is available. It is also available with us also. It is called a
Okay.
pallet
Okay.
plus. You can just have a
Okay.
search in that online.
Okay. Okay. Thank you.
Yeah.
Sir, what is the
Okay,
latest
sir.
project of 3D printing?
The latest advanced project is like a bioprinting,
Okay.
printing of tissues, cells, organs. It's advanced projects, and the current nominal product projects what it is going is in here is like in India is like aerospace projects are there, printing aerospace equipments and everything, and then food printing, like food processing 3D printing. Then drug printing is there, PCB printing is there. All these are new advanced researches going in 3D printing technology.
Okay. Thank you, sir.
Okay.
Okay, sir.
Hello, sir.
Yes,
Okay,
sir.
sir.
Yes, sir.
Sir, good afternoon, sir. I'm Gautam.
Yeah. Good
Actually, I have
afternoon.
one doubt, sir.
Yes, sir.
Sir, if you are doing a fusion deposition modeling process, what are the
Okay.
parameters you have to take, sir? What are the
Uh,
parameters and what are all
uh,
the tests you have to conduct in the particular component, sir?
the major
That
parameters
is,
I have explained in the slide itself. I think the build that layer height,
yes, sir.
then infill patterns, then support, then build orientation. These are all the major parameters. And the test after that, you can test. You can have the tests in like it's a composition. You can have the test in composition, XRD, then SEM test, microstructural analysis, and even you can go with fatigue and tensile compressive test. And even if you are going for a composite material, you can have effects of its degradations test, like oxidation test, all these things. As a
Yes,
research
sir.
part, I'm telling.
Yes, sir.
DSE tests
Sir,
are there, DSE tests are there, EDS tests are there.
yes, sir. Yes, sir. Sir, how the 3D printing is impact on education field, sir? Education
Actually,
applications.
education is having higher impact with by using 3D printer, because like as you know, like when we are studying, there was no tool like other than traditional manufacturing to make a prototype.
Yes, sir.
Considering
Yes, sir.
as a student, I'm limited to my budget. Actually, if I'm going with a project, I would not have a lot of budget in my hand to initiate my project, or to bring my project into life. So if you are going with the traditional manufacturing, injection molding or foundry techniques, or some CNC or something like that, it is so expensive, and no manufacturer will entertain for a prototype, or some single production, or single one-time order. But if we are going with the 3D printing technology, it is easily available. For the current scenario, it is easily available anywhere in our town, and it is very cheapest method of prototyping. All can afford it, because the material as well as the printer, even printer, we are manufacture printers from 17,000 till 20 lakhs machines are available with us. That 17,000 and 15,000 machines are even availed by school students. Even school students, they are having some competitions of making robots, drones, everything. They are very much into the project. Actually, from the schooling itself, they are into engineering, or those who are very much interested in engineering, they are starting from their school period itself. And now the scenario has been changed. Like if we take a project, and even the professors are telling, like make a live project, like a live prototype. So the only tool for prototyping, it is the real tool is 3D printing technology. No other
Thank you, sir.
prototype can give the pakka output.
Thank you, sir. Thank you.
Okay, okay, welcome, sir. Anybody is having any clarification?
Thank you, sir.
Okay, sir.
Thank you, thank you,
Okay,
thank
sir.
you.
Thank you. Okay, sir. Thank you for your valuable speeches in between the busy schedule.
Yes, it's okay,
Once
it's
again,
fine, sir.
I
Thank
thanks
you.
for all.
Yeah.
Now it's sir, close the PPT, sir, to take
Okay,
still
okay.
photos, sir.
Okay, sir. Thank you. You can have all can have my feedback of my session at Google itself. You can give a feedback in Google review. Like my company website is in Insta 3D Technology. You can just type Insta 3D Technologies Coimbatore. You can review in that itself. If you review in that my session, like it will be more like effective for myself as well as my company, and it is open to all. Like, so I just request you all to review my session in Google. You can just search Insta 3D Technologies Coimbatore.
Okay, sir.
Thank you for that.
Thank
Thank
you,
you.
sir.
Okay.
Dear participant, all of you unmute the video to take still photos. Sir, Basheer, sir. எடுத்துருங்க. Okay, thank you for the session. Thank you, participant. Next session to start at 12:10 p.m. So all of you attend the session. Okay, sir. Thank you. Thank you.